All right, so thanks everyone for, I can maybe kind of get rid of that. My name's Debbie Bard. I lead the Data Science Engagement Group at NERSC, and I'm going to be talking to you about Galactos, which is a project to solve what I consider, and I think what the field in general considers to be one of cosmology's hardest problems. I have the advantage of speaking slightly later in the day, so we already have had something of an overview about NERSC, so I can skip over all of this and spend more time talking about the actual science. But I should mention that the work that I'm presenting here was done running on Cori, which is our flagship supercomputer. It's largely a KNL-based supercomputer, currently sitting at number 8 in the top 500 list. So the title for these sessions is HPC in the environment, which I'm rather tickled by because cosmology is really taking a very broad view of the definition of environment. And so I'm trying to make sure I'm fitting into that theme. My background is in cosmology research, and one of the things that I really enjoy about cosmology research, there's a number of things. One is that we're trying to answer very fundamental questions about the nature of the universe. And the other is that I get to gaze at images like this almost for a living. And one of the aspects that I really like about looking at astronomical images is that when you're looking out at the sky, when you're looking out at stars, you're looking out at distant galaxies, you're effectively looking back in time. All astronomy is historical because the universe is vast and the speed of light is constant. And so the light from these distant galaxies that we see here in this image, for example, from the Hubble Space Telescope, we're seeing light emitted from the galaxies when the universe was only a few billion years old, perhaps. So we're really looking back in time as we're looking at more and more distant galaxies. We're seeing the state of the universe as it was when the universe was very young. And this is one of the reasons why we are trying to build wider and more powerful and deeper telescopes to allow us to see more distant objects, to allow us to get more information about what was going on in the early years of the universe. Because really understanding the history of the universe is key to understanding its nature. I'm going to talk you through a little bit about some of the real scientific effects of that. So there's kind of two questions that we're really talking about when we say, what do we mean by the nature of the universe? One is what the universe is made of, so what's in the universe. And the other are the major forces that are at play in the universe, so the physical laws that describe how the constituents interact. And this is, I think, one of the most mind-blowing graphics that we have in science today. This is our current estimation, our best guess about what the universe is made of. And the thing that is really rather astonishing is that everything we've ever seen, all the stars that we've observed, all the distant galaxies, all the gas and the dust out there, and everything around us, everything on Earth, this constitutes something like 5% of the content of the universe, and we consider this ordinary matter, although some of us still think that this is rather extraordinary. Something like 25% of the content of the universe is what we call dark matter. And I want to be very clear about the distinction between dark matter and dark energy, because I know the two are sometimes confused. Dark matter, we really do consider this to be matter. We think that it has mass because we see its gravitational effects. And the only reason it would have a gravitational effect is if it had mass. So we think that there is a proportion of the universe that is in some kind of dark, massive objects. It doesn't shine, though. We don't see it through our telescopes. It doesn't emit light. It doesn't interact with the electromagnetic spectrum as far as we can see. So this is why it's dark matter. Now, dark energy is a very different beast. Dark energy is the name that we give to a phenomenon that we have observed and that we have so far not a great explanation for. It's the phenomenon that causes the accelerated expansion of the universe. And we think that this makes up something like 68% of the energy content of the universe. And so this is a really exciting question from my point of view, is what is the nature of dark energy? What is dark matter? What are these things that make up the vast majority of our universe, but that we know very little about? And so I mentioned that we want to answer these kinds of questions, we have to understand also the forces that are going on in the universe and how those forces have been interacting throughout the history of the universe. And of course, the very early major player in the universe was the Big Bang and the subsequent period of inflation, which was a very rapid expansion in the size of the universe. And then after a time, the gravitational attraction of all the matter in the universe started to dominate. So at this point, the initial expansion due to the Big Bang, we think, started to slow down a little due to the gravitational attraction, the inward pull of all the matter in the universe. But then at some point, it appears that this deceleration was reversed and became an acceleration of the expansion of the universe. And the phenomenon that caused that is what we call dark energy. And then graphically speaking, this is kind of what it looks like. So you start off with a Big Bang, you have this period of inflation, kind of slows down and then starts to speed up again. And we're somewhere around here in the present day. We've no idea what's going to go on in the future. We don't know whether the universe is going to keep expanding forever or it's going to contract. We have a lot of different theoretical models that make these kinds of predictions, though. And a lot of our work as cosmologists is trying to understand what those theoretical predictions are really telling us and how we can compare those theoretical predictions to our observations of the universe and understand something about which model best describes what we see when we look out at the sky. So how do we actually measure this? What are the observations that we take in order to understand something about the nature of the universe? Well, at the moment, we really talk about the expansion of the universe being driven by these two competing forces, the gravitational contraction of matter pulling matter into more clustered, more structure, and the expansion of space itself due to dark energy. And I make this distinction quite clearly that gravity is contracting matter, pulling matter together, whereas dark energy, as far as we understand it, is expanding space-time itself. So it's not making matter, it's not making us get any bigger, it's expanding space-time. And these two forces and how they interplay together and the various physical models that describe them, that could describe them, leaves an imprint on the distribution of matter in the universe that we can observe. And there's a number of different ways that we can make these observations, and what I'm really talking about is observing the distribution of matter. And in this set of timestamps from snapshots from a cosmological simulation, you can kind of see how that comes together. So over time, you start off with a simulation box with some distribution of dark matter. Over time, the box gets bigger as dark energy forces the expansion of the universe. But the matter gets clustered together, gets clumpier as gravity is pulling it together. So in an animated form, it looks something like this. And when we're running these simulations, we run them with different physical models that describe gravity, that describe dark energy, that describe dark matter. And so this is an example of a snapshot of a simulation, the same initial conditions, but changing just one physical parameter. And you can see that the distribution of matter, the clustering of matter, looks pretty different between these two different models. And I want you to remember this when you look at, when we're talking later about the statistics of how we describe the distribution of matter statistically. This is something I think is a really useful way of visualizing it. In some models, the matter is more evenly distributed, and in some models, matter is more clumpy. It's more clustered on small scales, and that's something that will be important to remember in a few slides' time. So that's not just something that we see in simulations, we see this in our data as well. So this is an image from the 2DF Galaxy Redshift survey. 2DF stands for 2-degree field. It was surveying a relatively small area of the sky and looking at the locations of galaxies. When we talk about galaxy surveys or galaxy redshift surveys, we're really doing a census of the galaxies, mapping them in space. Where are they in space, and how far away are they from us, which is also a mapping of time, of course. So this is us sitting here observing, looking out into the sky. You can see the locations of galaxies that are closer to us are more tightly clustered than the galaxies that are further away. And so this is a survey that covered something like 1.5–2 billion years of time. And so as we're looking at galaxies further away, you can see how the structure of the clustering of the galaxies has changed over time. So in the images I'm showing here, these are dark matter simulations where we're simulating both dark matter and the locations of galaxies. But when we're doing a galaxy survey, we're using just galaxies which are really good traces of the dark matter distribution. As you can see here, the patterns of the galaxy locations matches the kinds of patterns you get in your dark matter simulations. So even though we can't, using this methodology, we can't look at where the dark matter is directly, we can see where the galaxies are tracing the dark matter distribution and use that as our observation. Okay, so I want to just spend a little moment talking about Redshift. It's a concept that is pretty well understood, I think, in general, but from a cosmologist point of view, there are some subtleties in this and some confounding factors that we have to consider when we're looking at Redshift surveys. So a redshift is basically like the Doppler effect for sound, but with light. Objects that are moving away from us have their light stretched out, and as that light is stretched out, it appears more red. So just as a car moving away from you, or a siren on an ambulance or something moving away from you, the tone of that siren drops, it gets more stretched out as it passes. So as galaxies are moving away from us, as any light source moves away from us, its light becomes more red. And this is basically how we know that the universe is expanding at all. When as astronomers we look out at the sky and we look at the light that we see from all the stars around us and all the galaxies around us, we see that everything is redshifted. Light from all the galaxies, every galaxy we see is redshifted. And that either means that we are sitting right at the center of the universe and everything is rushing away from us as fast as it can, or the entire universe is expanding and everything is moving away from everything else. And the latter seems a more likely explanation. And it was in fact this observation that everything is moving away from us and that the things that are further away from us are moving away from us at an accelerated pace. That was how the observation of dark energy was first made, and that's what won the Nobel Prize a few years ago. But the expanding universe is not the only source of redshift. Galaxies are interacting with the other galaxies around them, other massive structures around them. They're constantly moving around under local gravitational effects as well. And this means that if, from a cosmologist point of view, if you only care about dark energy, then this is going to be a very pesky effect where your measurement of the galaxy redshift is being infected by this redshift space distortions, as it's termed, RSDs, where your observation of the nice distribution of matter in the universe is going to be distorted in the way shown in this little animation. And from a cosmologist point of view, this is an irritation because you have to try to back that out from your measurements. You have to try to correct for that in your observations. So that's an irritant. You have to account for redshift space distortion when you're trying to interpret the structure of the universe. But if you're someone who also cares about the nature of gravity and someone who also cares about having the big picture, really understanding everything that's going on in the universe, then this is a very useful effect. You can use redshift space distortions to learn something about the nature of gravity on these smaller scales and learn something about how galaxy clusters are interacting. And that's really important because gravity is a big player in the expansion of the universe. It's not simply that dark energy is moving everything apart. You also want to understand the nature of gravity. So for this reason, redshift space distortions are kind of becoming a hot topic in cosmology. It's something that we're trying to measure, we're trying to understand. But it's something that's relatively new, and there are a number of reasons why it hasn't been attempted before, but the project that I'll be presenting is a really nice way of taking this into account. Okay, so now I'm going to talk a little bit about statistics without going into any equations. I want to talk about how we characterize the structure of matter in the universe, the statistics we use from our observations to actually do this measurement. And one of these big statistics is the power spectrum. So the power spectrum basically measures Gaussian fluctuations in the matter density field. This is sort of what it looks like in graph form. This is inverse distance, so this is on small scales and this is on large scales. We measure this in galaxy surveys by measuring the 2-point correlation function, where we count pairs of galaxies at different distance scales and compare those pair counts to pair counts that you would see in a random distribution. And so at different distance scales, you might be measuring the power spectrum on smaller distances or larger distances. That's how you build up this picture of the power spectrum of the matter in the universe at all scales. Now, this is a computation that scales as order n squared, where n is the number of galaxies. So it's not a trivial thing to calculate, but it's a relatively computationally affordable statistic to calculate. When I was just looking at the archive for papers that use the 2-point correlation function, there are thousands upon thousands of papers based on this measurement. This is a standard measurement for astronomical surveys. It's a standard measurement for theoreticians. And it really does tell us a lot about the structure of matter in the universe and how it's distributed. But it's only one statistic, and there are many other statistics that can give us more information. And one that I feel is sadly neglected is a 3-point correlation function. So in the 3-point correlation function, very similar to the 2-point function, except now you're counting triplets of galaxies. And a reason why this is really interesting from a scientific point of view is that instead of just looking at basically a one-dimensional distance, you now are looking at a 2-dimensional surface. So you've added a dimension into your calculations that gives you information about non-Gaussianities. So this tells you something about perhaps distribution of matter during inflation and some inflationary effects that could come in and influence the initial distribution of matter, which would then be carried forward as the universe evolves and dark matter and dark energy are doing their dance. An example for this is shown in this nice figure where we're comparing theoretical predictions with different measurements. And if you look at the 2-point function, both of these cases, you have really nice agreement between theory and measurement. But if you go to the 3-point function, you can see that only one of these matches. In this case, the measurements are very different to the theoretical predictions. And so there's a real power in the 3-point function to get into some of the subtleties of the physical model describing the universe. Unfortunately, you're counting triplets of galaxies here, and this is a computation that scales as order n cubed. And it is largely for this reason that the 3-point correlation function is so rarely used. So when I did the same search on arXiv looking for papers describing the 3-point function, I found 382. And of that 382, I'd say 381 are theoretical papers telling us how important the 3-point correlation function is and how valuable it would be to measure it. There are very few real measurements made of this function with real data. It's just considered to be too computationally difficult. So that's where our project comes in. The project Galactos, we're measuring the 3-point correlation function at scale using a really, I think a really valuable combination of innovative new algorithms from theoretical physicists combined with a very smart partitioning of the problem across multiple compute nodes using a KD tree, and then combined with very well-optimized single node code that actually does the calculations at very high efficiency. And I think without any one of those 3 parts, this would not have worked. It's been a very satisfying collaboration from my point of view between the theorists, the physicists, and the Intel experts who worked on the single node optimization, and our NERSC experts who worked on the MPI implementation. So I'm just going to go a little bit through what some of these innovations were. So on the algorithmic side, Zach Slepin and Daniel Eisenstein came up with this new way of formalizing the 3-point correlation function, which was using a tremendous amount of math, which I'm not going to go into here at all, partly because I don't understand all of it. But they used a spherical harmonic addition theorem to reduce the 3-point correlation function to a product of spherical harmonics, which depends only on one triangle side, because math, and therefore you only need 2 galaxies to calculate this function rather than 3. So already by rethinking the problem mathematically, they've turned this into an order n squared problem rather than an n cubed problem. But not only that, there's also the concept of directionality in this theorem. So you are aware that the idea of the directionality, the line of sight from the observer to where the galaxies are, is included in this, which allows measurement of redshift space distortions simultaneously with the measurement of the large-scale expansion of the universe. And this is something that's really new, and I think is really exciting from the theoretical point of view. So then we had multi-node optimizations using an asymmetric KD tree to place the galaxy pairs in their distance bins. This is an MPI distributed KD tree which partitions space into unequal volumes but equal numbers of galaxies. This is to ensure that we had a very load balanced running with our code. Each volume has its own MPI subcommunicator, and a key stage in this was neighbor exchange in the MPI processes. And this is to really load balance the MPI processes. So each MPI process gathered the neighbor galaxies from the next distance bin surrounding it. So this means that you have more galaxies, you have galaxies that are duplicated across many MPI processes, but as the data load for this, this calculation is fairly low, this is something that we can tolerate. And it means that we have an almost communication-free implementation, which means that it scales very well. After this initial first step of distributing all the data that's needed on all the compute nodes, then we have a very highly efficient, scalable code. The single node optimizations were performed by our Intel partners, focusing on thread parallelism over galaxies and ensuring that we had vectorization of the galaxy pair calculations and very efficient memory reuse. I can talk to you more about some of the details of this later on. But we ended up, after some considerable work on all sides, with very nice performance. So we ran using a data set from the simulation which consisted of something like 2 billion galaxies, and we are able to achieve almost perfect strong scaling, almost perfect weak scaling. Please note the truncated axes here. We're able to calculate the anisotropic 3-point correlation function for 2 billion galaxies in about 20 minutes on all of Cori. With almost perfect scaling, we achieved something like 5 petaflops sustained performance and a peak of around 10 petaflops. And this is important because the previous, I think, largest attempt at calculating the 3-point correlation function was on something on the order of 200,000 galaxies. So we're really taking this orders of magnitude further and scaling this out even beyond what people are even thinking about doing today. And so, for me as a cosmologist, this is really why this is an exciting project to be involved in, because we're able to compute the 3-point correlation function for basically all the galaxies in the observable universe in less than a day with this. And I think it really turns the 3-point correlation function into a usable statistic for cosmology. And we're working on some follow-up science papers for this, and it's something that I'm personally very excited about. So I wanted to say thank you, and also thank you for the award of the Innovation Excellence Awards from Hyperion Research that we got this year. We're very proud of this as well. Thank you.